So it's 7 o'clock. Who has questions?
You explain like what's called like carboxy terminal.
Oh, yeah. So basically, with carboxy termini and N termini, when you click all your amino acids together, you're going to have one end that's a carboxylic acid and one end that's an amine. And so when you're looking at the 3D structure, like from the homework, the arrow is always going to be pointing towards the carboxy because that's like the front of the protein. Because when you hook on, you're going to keep hooking onto the amino terminus.
So it's like doing it's just like a big like wiggle.
Yeah.
How do you find it in that? Like the one on the left is carboxy, the one on the right is amine.
So
I feel like I've never seen it. Okay. Wait, it's adding to. Why is it something? Like it's just pointing to start. Okay.
that's not something you'll need to know super in detail. Like you should know how to do the amino acid chains where like he gives you letters and you hook them together based on what those letters are. But that stuff is a little bit more complicated than we'll need. Yeah. Yes. Just like a very general. The cofactor chemistry. So that's like your NADH reductions, your NAD oxidations, your thiamine decarboxylations, and the PLP stuff. Yes. Or like the homework where it was like draw out a decarboxylation using thiamine. Yeah. Okay. So the main thing you want to know for PLP is it's going to help you form amines. So PLP chemistry you can associate with amines in the same way that you can associate your thiamine chemistry with decarboxylation. And your NADH chemistry with reduction. I'm pretty sure those are the three cofactors that we've covered. So, how many chiral centers do we have?
Sorry, decarboxylation, what is that like? What reaction is that?
So decarboxylation is when you lose CO2. So that's yes, I guess it would be because it doesn't really fall under any of the other 12 that you have learned. So, I can. Oh, okay. I have to say the microphone feels a little bit intimidating. I'm not a professor, I'm just a girl. Okay. So, does that help? Okay, cool. Hallie, does that answer your question? Okay. Any other questions before we get on to moving to answer this question? Cool. So this is what we are going to do the amine formation on, and then we need our actual PLP. So I'll draw it in a different color so it stands out. But PLP is a cofactor that you are going to use with an enzyme. And so it is bound to an enzyme. So when we draw it out, we have this N that's connected to an enzyme. I would say be able to recognize it but I don't think that you need to memorize it. So the first stage is a transamination, which is one of the 12 reactions that we covered. So the first thing we're going to do is transamination. This means that we are going to take the lone pair that's on this nitrogen. It's going to attack all the way over here, like this. And then we're going to make an enzyme bound intermediate. And that basically means that now our whole structure is also bound to the enzyme. This is going to be kind of an ugly drawing, but it'll get the image across. Yes. So once I finish drawing this, I'll break down the arrows step by step. So now this is attached here. So breaking down exactly what just happened. Our first arrow is going to be the amine attacks our alkene. Actually, it's not an alkene, it's an imine. That overloads this carbon. So we're going to have to push electrons onto the nitrogen. And we doubly like that because putting those electrons back onto the nitrogen are going to neutralize out this charge. So we neutralize our nitrogen. And this is the intermediate we get. So from here, we're going to see a deprotonation. So we'll say X minus comes in and gives those electrons back to the nitrogen. So now it's neutralized. And in that same move, we're also going to put a nitrogen or put a hydrogen on our other nitrogen. And this is called tautomerization. So basically this proton moved to this nitrogen. So we took it from one place and put it somewhere else. And so the basic definition of a tautomerization is you're changing the connectivity, but you're not changing the chemical formula. So like if we were to longhand write out our chemical formula here, it would be like C12N3O4H8. We're not changing that. So we're having the same amount of protons, the same amount of oxygens, the same amount of carbons. We're just changing the connectivity a little bit. So you can think about it in our case as really just a proton transfer, because for the most part, all your tautomerizations will just be taking a proton from one nitrogen to the other, because all the tautomerizations you have learned have been in the amine formation world. So Now we have a lone pair on this nitrogen, which we can move here and neutralize the positive that was created on this nitrogen in the tautomerization. So now we have an imine attached to our PLP. So, right, we've taken it off the enzyme. It's now attached to the thing we're going to do chemistry on. So our cofactor is now like ready to help. So this was all the first step. This was that transamination. So now we can actually do the amino acid modification. And we use PLP to help stabilize a carbon anion. So we're going to form our carbon anion. So that means taking an acid and deprotonating. Taking a base and deprotonating. So now we no longer have chirality because we only have 3 substituents on that carbon. Yes, no, maybe so. Following? Okay. So with this anion, we can protonate at the other chiral site. So you see how this was, or actually I'll highlight it. We have the wedge on our PLP and the like dashed wedge on our proton. So the dashed wedge is like behind us. So the proton is like going outside the building while the PLP is coming at you guys. So now that we've taken that proton off, we're going to put it back on from the front. So we'll have some H plus here that our anion will attack, and the resulting structure will give us a wedge to the N and a block to the H. So our amino acid has been modified. Now we are going to release it from the PLP. And basically, that is just going to be a transamination going the other way. So we did a transamination to get the PLP off the enzyme and onto our amino acid. Now we're going to do another transamination to get it off the amino acid and back onto the enzyme. And so for that, we're going to follow basically the same steps we did before. So we have our amine that's attached to the enzyme. And this is the same. This is the same as this one. I just didn't draw it in the steps where we didn't use it, but it was still hanging out. So it has a lone pair that is going to attach or attack. Let me do this in green. Attack the carbon of our amine, because remember that acyls, they have that electrophilic difference where your heteroatom will be slightly negative and your carbon will be slightly positive. So that's why it attacks there. And those electrons will push onto our nitrogen center. So that is going to give us the whole thing attached to the protein now. It's kind of ugly drawn, but it'll have to do it. So now we are going to do a tautomerization where we're going to take this proton and put it on this nitrogen. Now our enzyme nitrogen has a lone pair again, which means that it can form the amine and release the amino acid. So we're going to be left with our new amino acid. And we will have our enzyme-bound PLP. And that's it. Yes.
You said blank, so now I can understand that. What does it have to do with the?
So this lone pair is going to form the amine. So it forms a double bond with this carbon. And then that carbon will be overloaded. So it's going to return the electrons back to the nitrogen, and that releases the whole amino acid. So that is like the middle part of this. So for PLP, you basically have transamination and then the actual chemistry and then transamination. And so what we're doing is we're making this anion. Now, when we have an anion, we only have 3 substituents. So there's no chirality there. And because this is an enzyme, enzymes are very specific. So it is going to attach the hydrogen from the front now. What? The step before it is deprotonation by some kind of base that's in the solution. Yes. And the reason that we're able to change chirality is because in an enzyme, there are very specific amino acids, and all of their positioning is very, very, very specific. Like the active site has this down to a science. And it will pluck off the proton. It has a basic amino acid, so something that's ready to take a proton, positioned at the back to take off the back-facing one. And then it has a protonated amino acid that will give it the front one. Other questions?
You just.
Yes, I will post this document that I have been drawing on, and then I'm recording it, and hopefully it will turn out like the other one did.
So is this what you're developing mechanism?
Yes.
And would we have to go like this? Develop-
So you probably would not have to do a mechanism of an enzymatic reaction, but you should know the first and the last steps because those are transamination reactions, which are one of the 12 that we've learned. Yeah.
Oh, sorry. Justin, any, I mean,
Yes. Carbons and hydrogens.
they can, like that's what they are.
They either have to be like a carbon or a hydrogen. No, because carboxylic acid has two O's and a ketone needs to have two. So, yes. Ester has to be another carbon. And then this is technically also an acyl. And then you have ethers, which is
What is the C1 refer to again?
acyl.
Yeah, because I remember you said like you're doing like the, I don't know how to describe it, but you like went through the like the last three letters, like one that's like double bond. You know what I mean?
Yes, so that doesn't, acyl is not one of those. Acyl, like, in general, just means these double bonded oxygen compounds. But I think what you're talking about is aldol,
Oh,
where ald is aldehyde because those reactions were first discovered only using aldehydes, which we know now that those reactions also work with ketones and like other acyls, but when they were discovered, they only worked on, or they were discovered with aldehydes. So that's where the ald comes from. And then the ol, like the OL, comes from alcohol because an aldol addition makes a aldehyde and an alcohol initially. But now they make ketones and alcohols.
we go over question 4.
Yes. Yes. Okay. So, first step, what functional groups can you identify? Acyl. And initially we had this S-CoA attached, and at the end we have this amine attached. So basically we substituted our S-CoA for the amine group. So this is an acyl substitution. So what changed between structure 2 and structure 3? So we had this is a ketone, and we went no. So that is what kind of reaction? Reduction. What happens when we add to an alkene? So our change was an addition to an alkene. So this is electrophilic addition because we added a bromine. Yes, in this case, yes. Yeah. A proton. So you can assume it depends on what was used as a reactant. So if it was Br2, this can break up into Br plus and Br minus. And so it could have been an electrophilic addition starting with that Br plus. It also could have been an electrophilic addition starting with the proton. I guess no, because you could do a nucleophilic addition using Br minus and it would get you the same product. So our next structure what kind of species is this? A nucleophile. Why? Yes. So this lone pair makes it electron rich, which means it's a nucleophile. What happened to our bromine? It got substituted. So we have a nucleophile participating in a substitution. Any guesses on what kind of reaction we have? Okay, I was gonna say, guys, I walked you right through it. So this is nucleophilic substitution. And our final step, we add this carbon chain. What is so special about this ring? It's aromatic. So what kind of reaction do we think this is? Yes. Because this OPP leaving group leaves as OPP minus. So it'll create a cation on the carbon. That's not right. It'll create a cation on the carbon because it'll leave like this. So it'll take the electrons with it when it leaves and generate a cation. Cations are positive, cat positive. And so they are electron deficient, meaning they would like more electrons, so they're electrophilic.
So if we see OPP, would be safe to assume electrophilic substitution, or just the electrophilic parts?
Yes, yeah. You can, when you see OPP, you can think of it as a leaving group where it takes the electrons with it. What's up?
How is it a substitution?
So it's because we substituted the proton that was here. This one.
It's a base code.
So the mechanism for electrophilic aromatic substitution is on the study guide if you want to review it. But a base is not needed for electrophilic aromatic substitution because the whole point behind aromaticity is an aromatic compound is really stable. And so rather than needing a base to deprotonate it, the electrophile is going to attack. And then there's two options. We could protonate, well, we would need a hydride. But anyway, we could add a proton to the carbocation we created or we could lose the proton that's at the site we just added to and lose or put the resulting electrons back into the system, creating an aromatic system again. So we don't actually need a base. That proton is going to have a super low pKa and it's basically going to fall off.
Why is between 2 and 3 reduction?
Anytime you see a double bonded oxygen go to a single bonded with a proton, that is a reduction.
So double bond oxygen, single bond proton.
Yes. Basically, carboxylic acid to aldehyde / ketone to alcohol is always going to be a reduction. And the same way where you go backwards, it's an oxidation. So if you go alcohol to aldehyde or ketone to carboxylic acid, will be an oxidation.
So alcohol to
Aldehyde or ketone,
there's a first step.
carboxylic acid.
So you have to do all.
You don't have to do all three, but like they move in that order. So if we could have, we can't really oxidize at this site, but there's another site that we could have reduced at. Which one? Yes. And there's another one. The carboxylic acid. So this would be reduced to an aldehyde, and then it could be reduced to an alcohol. Whereas if we were doing an oxidation, we could oxidize this alcohol to an aldehyde. That would be complicated because it's on an aromatic ring, but that's besides the point.
Wait, so sorry, was it alcohol to ketone?
I think I have it in. So in the study guide, oxidation reactions, a good example to know, it has written out for you, alcohol to aldehyde to carboxylic acid. And then if you need help remembering what those are, if you scroll to the bottom, I go over the functional groups and you can see what's an alcohol, what's an aldehyde, and what's a carboxylic acid. You don't need to know the mechanism. Yeah.
There was a question.
I'm not sure, but I do think that type of question would definitely be on it. And I think it could get grouped with NMR to help you determine which product if there are multiple. Other questions? Mm-hmm. Yeah, so when we have a basic alkene like this is symmetrical in many ways. It's symmetrical this way, it's also symmetrical this way. So when you're having the breakdown of that bond, the electrons could end up, we'll say that's too close. We'll say this is carbon A, and this is carbon B. The electrons are equally as likely to end up on A as B. So This isn't a great example because they're symmetrical. They're too symmetrical. So let me change this a little bit. So because it's all hydrocarbons, there's no real pulling force for the electrons. So they could end up on either carbon. Meanwhile, if we had an alkene that looks like this, actually, yeah, we'll do that. Electronegative atoms like oxygen or nitrogen or sulfur are better at stabilizing changes in electron charge. So they're better at holding on a negative charge or a positive charge. They're a little bit more loosey-goosey with their orbitals than carbon is. So with this particular molecule, we would see the breakdown like this. Where we form a negative charge here because it'll be more stabilized by that oxygen. So I would say the rule of thumb here is your negative will end up closer to those electronegative atoms. And so that's what you need to think about when you're deciding which side will be your nucleophilic side and which side will be your electrophilic side. Other questions? What? Yeah. So do you want like a structural explanation or do you want like a mechanism? Okay. Redox or oxidation first, or reduction or oxidation first? Oxidation. So oxidation, you don't super have to know. I would say know the mechanism with NADH, but also be able to recognize other oxidizing agents. So if you are given like an aldehyde to a carboxylic acid and it says that O2 is present, you know that that is an oxidation because O2 is an oxidizing agent. But you don't need to know the mechanism with O2, but we'll go through the mechanism with NAD plus because you will use NADH mechanisms for reduction. So
NAD plus the same thing as
NAD plus is the reduced version. Or is it the oxidized version? Yes, it's the reduced version of NADH. So the first thing we're going to see is a deprotonation. This is going to force electrons onto the oxygen, which will force them off of this one. This oxygen, the way we've drawn it now, would be overloaded. So we are going to get rid of our entire hydride, but it needs somewhere to go. So that's where NAD plus comes in. And this hydride will come here and will push the electrons down in the system until it neutralizes the nitrogen. And we are left with our oxidized product. And NADH. So this is one of the ones that's a lot of arrows in one step.
So the oxidizing of oxidizing agent
Mhm.
is the NAD+.
Yes. It could be another one. Could OH reduce NADH or NAD plus? No. Because water breaks down into a proton and OH minus. In order to reduce NAD, you need a hydride. So this is a proton, and that's H plus. So it's a hydrogen with no electrons. But H minus is a hydride, and that is a hydrogen with electrons. So here, we're moving the electrons with the hydrogen, not just the hydrogen. So it's a hydride. Other questions? Yeah. Only with reductions. Specifically with, or only with oxidations where you're reducing NAD. Because NAD is the only hydride acceptor that you know of, and it's NADH is the only hydride giver that you know of. So the hydride stuff will only happen with NADH or NAD.
You flip the arrow, it's gonna change.
Yeah. The like exact reverse of this reaction would be a reduction.
I think it's like homework 6 or 7 where they have like a chart that had like files and like files.
Yeah. I hesitate only because that can really go on forever. Like I could give you a million nucleophiles and a million electrophiles.
So would it nucleophile be the oxidizing agent or the reducing agent?
Neither. So nucleophiles don't really have a play in this. If you really needed to point out a nucleophile in this specific reaction, it would be the base that's doing the initial deprotonation.
explain a question like the last one on the last prelim? Where like you have to find.
Yes, but let me pull up this one. So on the actual prelim, were you given the name of the reaction or were you just given the, okay. Actually. So we know that this is going to be an electrophilic addition. What do we need to do an electrophilic addition? An electrophile. So we're going to need to make an electrophile. How do we do that? We'll break up our HBr. There are two different electrophilic A reactions you could do here. You could do electrophilic addition. You could also do electrophilic aromatic substitution. So we know that this is going to be electrophilic addition. So we're going to add to an alkene. All of the alkenes that are in this ring aren't thought of as individual alkenes, but they're thought of as the entire aromatic system. So we wouldn't do additions on any of these alkenes. We would do additions on the alkene that's off to the edge. Now, Julia, what was that question you asked earlier about alkenes? Yes. Yeah, knowing where to do the substitution. And what did I say is our directing point? Like, what do we look for when we're trying to decide which part of the alkene it's going to go onto? Yeah, electronegative atoms. Are there any electronegative atoms in this molecule? No. So we would see formation of both of these products. Yes, no, maybe so. Thumbs up, middle down. Down. Okay. Okay, that's okay. Do you want me to break it down as a mechanism? Okay. So with our alkene, we can make two different species. And the difference between these two are where the electrons from our alkene, where the electrons from the pi bond in our alkene are ending up. So they could go to this carbon and make this structure. They could go to this carbon and make this structure. because we don't have any electronegative atoms in this molecule, we don't have any directors pointing those electrons in any specific way. So we are equally as likely to get both of these two structures. And with both of these two structures, we have our H plus and our Br minus. We have two different products that we can make. So we could have our alkene attacking the proton and creating the carbocation. So this will become these. And from here, our bromine can attack here, or on the other one, it can attack at the bottom. And so it makes two different molecules.
How did you know the bromine was negative?
Because when HBr breaks up, this is the like chemical structure of HBr. The electrons go here. And so our ionization is H plus and Br minus, kind of in the same way as water, where we have the ionization as H plus and OH minus.
So why didn't HBr like stay bonded together where they were at?
So HBr is one of those with a very low pKa. So all of your halogenated acids. So halogens is that like last row before your noble gases. So that's like bromine, chlorine, iodine. Those are going to ionize really easily. So hydrobromic acid, which is this, hydrochloric acid, which is HCl. And you probably won't use it, but if you do, iodic acid, which is HI, those all break apart pretty easily. And so because they're strong acids, they exist more in the ionized form than in the connected form. And that's how the exam is cumulative, because this is pKa stuff from January. So it all built on itself. And even if you don't feel like it's cumulative, it is. Yeah. Leaving so soon, Francesca? Okay. Problem set 9. Question 2. So this question took a lot of research or perhaps Googling. Because you had to figure out what disulfide bonds were and bridging across alpha helices. I do think that this is more complicated than you would need on the exam, because you definitely needed a computer to answer this question. But yeah, so like breaking down the information that you're given, you have hair consists of long protein keratin filaments and derives its rigidity from cross-linking between them. Breaking down that sentence into the parts that you need in answering the question. You have long protein. So protein is something we've been covering. we recognize protein as a sequence of amino acids. And it derives its rigidity, so it's like firm structure, from cross-linking between them. So that means connections across our amino acid chains. A perm is achieved by treating hair with perm salt followed by a neutralizer. What is the structure of perm salt, and what does its structure tell you about the nature of the crosslinks between keratin molecules in hair? So when you look up perm salt, you found a thiol and a carboxylic acid with an amine, and then the neutralizer is H2O2, which you might, recognize as hydrogen peroxide. So from that, you can see a thiol, which is a group that we see in amino acids, and a carboxylic acid group. So remember that our basic structure for carboxylic acids is we have the or our basic structure for amino acids is that carboxylic acid and that amine group. That's like your basic structure. And then the R groups are where you have differences between all of your amino acids. And so in the perm salt, you see the carboxylic acid, you see the amine, and the only thing that's left is that thiol. So you're thinking about R groups that are thiols. So when you look up the structure of a perm salt, it would show you that structure. The stuff about amino acids is, I don't know what lecture it's from exactly, but whatever lecture where we first introduced amino acids. Okay, so when you're looking at the sequencing, you are going to see so the appearance of C is a cysteine amino acid, and cysteine amino acids have a thiol group. So they have that sulfide or sulfur that can make the cross-linking. And so it was recognizing that motif in there, but that is kind of difficult to find for people who don't do protein chemistry. What? So the sequences, like, yes, we have gone over, but never in this complexity. I don't know. I don't think you'll need to know an ISO work. Okay. I think your energy for studying would be better focused on learning mechanisms and being able to identify them in other contexts. And if you're like really pressed about learning protein and amino acid stuff, knowing how to take like a 4-letter sequence, like he gave you, I think he's given you chem and rain, and being able to form those if given an amino acid table. Yes. So that's basically question 3 from homework 9. So we'll cover that. So you're given this sequence of rain. The 1-letter code for these amino acids is given here. So R is arginine. So you don't have to have that memorized. It will be given to you. A is alanine. I is isoleucine. I, unfortunately, have to Google what N is. Asparagine. So now that you know what 4 amino acids you have, you can go to your little table and you can look up what those R groups on them are. That's what R's. So you can kind of just start with the basic shape of an amino acid and then fill in the R groups later. So we know that, well, let me simplify that. That's your basic amino acid structure. Technically NH2. So we are going to be hooking 4 of these together. And how we do that is the formation of amide bonds. So when we hook all of these together, we're basically going to replace this OH with a connection to this amine. And we're going to do that down every single peptide or every single amino acid. So this becomes NH. And we have our R1 here and our R2 here. We're going to replace now this OH with the next NH. And we're going to repeat it one more time with our last one. And because we have no other amine to add on, this one will end in the carboxylic acid. So that would be our basic structure. Now we can go in and add our R groups according to which amino acids are involved in our chain. So the R group for R, which is arginine, is 1, 2, 3, 4, 5, a 5 carbon chain. 1, 2, 3, 4, 5. Sorry, this is kind of cramped, but it'll get the picture across. So that's our R. Now we can move to our A. Alanine is one of your most basic amino acids. Its R group is just a CH3. So we just add our CH3. Next, we'll move to our isoleucine, or our N. And this is going to be a connector between a 4 carbon chain. 1, 2, 4. This will then attach to our final amino acid, which is N, or asparagine. And it has the R group of this. I was going to say it, but what's this functional group called? Anyone other than Macy? Amide. So now we have, if we were to break this down, we have R, and then the last part of this question was identifying your amino and carboxy termini. And so you have carboxy and amino. Because this is an amine group, and this is basically a carboxylic acid. Mhm. Yes, so if it was drawn in the 3D, your beta sheets would point like that.
Which way does it add on to, like, it adds on to carboxy?
You aren't studying protein synthesis, so you don't really need to know which side it adds on to, because for the most part, you'll just be given, okay, these are the 4 amino acids you need to click together.
Okay.
So I wouldn't worry about it. Yeah.
Why did you add it?
What do you mean? This is the R group for that, and this is the R group for that. So they don't have any hetero atoms, but they are still R groups. No. We are not going to do that one because I don't think you will need it for the final. The main point there is you're doing multiple low energy steps rather than one big energy step. And the most energy you take is going to be the slowest step in your reaction.
Would we be potentially asked if, like, given this, match it to the correct? They're like,
Probably not.
is there anything else we need to know?
Probably not. Yeah.
Would you say a good portion of the final would be just understanding mechanisms or reactions that are not over and the fundamentals behind them, such as chirality?
Mhm. You've gotten a lot of homework questions that are like, identify this reaction or draw the product of this. I would expect similar questions on your final. It probably won't be the whole entirety of your final, but that is like the core information that you are meant to take away from this class.
If we're expected to write the product, it will tell us what kind of reaction it is. Or it will have all of the necessary parts to identify what it is.
Yes. How are we feeling? Okay.
Is terrified a good answer?
Okay. Everybody is shooting for mediocrity. I love to hear it. Yeah.
I was gonna say, maybe you could just like throw a random reaction. You have to find out unless that's the bad one.
Yes.
I don't know if I'm smart enough to come up with a random reaction off the dome.
one and show it to us?
There's a lot.
Yeah, there is a lot in the resource guide. There's a lot of practice problems, and I also put some YouTube videos up there. If you don't like hearing my explanations, you can listen to crash course explanations, because I think a majority of the YouTube videos I put on there are from crash course. Other questions? Things you want to review? I know I haven't done a recorded review of NMR. I was thinking about doing that tonight, unless everyone here is like, nah, I'm great at NMR, and then I would do it tomorrow. Yes to NMR? Okay. Question or yes to NMR? Okay.
Very specific questions I can
Okay. Yes. I'll do Claisen reactions after NMR. Okay. So for NMR, I'm going to use problem set 5, question 5. So my strategy with NMR is to extract all the possible information I can out of the structure before I even look at the spectrum. So I want to know what I'm looking for when I finally do look at the spectrum. So with this one, the structure that we're given is this. So my rule of thumb with NMR, there's a workflow that we can go through. So the first is identifying our proton groups. Then we will look at integration or intensity. Then we look at multiplicity, which in simpler words is splitting. Then we look at the chemical shift. And then we can actually assign our peaks. So the first thing I'm going to do with this structure is I'm going to draw out all of our implicit hydrogens, just to make sure that I am aware of all of them. So on the end here, we have a methyl group, which means there are 3 implied hydrogens. This carbon has 4 bonds, so it has none. And our other carbons in our ring will have 1. Here we have another methyl. This carbon only has 3 bonds, so it will have 1 as well. This carbon has 4 bonds, so it has none. Same with this one. So 3 lines is alkene, but more, right? So it's a triple bond instead of a double bond. And it basically just means that there are now 2 pi bonds in addition to our sigma bond instead of 1 pi bond in addition to our sigma bond. So we have all of our protons drawn out. So our first step, according to my little workflow here, is identifying the proton groups. So how many proton groups do you think we should have here? Yes. Why? So we have A, B, C, D, E, and F. So we have identified our proton groups. Any questions about how we grouped these together?
How come the two that are in C are the same?
So that is because we have a line of symmetry down our aromatic ring. But it is symmetrical because we could cut these bonds in half. And so these two protons see the exact same thing. Like we could fold our benzene ring like on a piece of paper, and those two protons would end up right on top of each other. You mean why they aren't the same horizontally and they are the same vertically?
Like I understand the benzene ring is symmetrical,
Yes.
but the DEF.
Yes. So because of chirality, that can turn, and so it is symmetrical. So these are our proton groups. Our next step, we have now identified our proton groups. Our next step is integration or intensity. And another way to think about integration or intensity is how many protons is each signal speaking for. So for A, how many protons are in proton group A? 3. So we would expect an integration of 3. How many are in proton group B? 2. C, D, E, F, bam, integration done.
Is that how tall it is?
Yes. So intensity is how tall it is. And with a singlet, that's all that matters is how tall it is. But if you have a splitting where you have like a wider peak, so it looks like this, integration basically means the area under that peak. And it means that although this is kind of shorter and wider, it could have the same integration or the same area under the peak as something that's really tall and skinny. So our integration is done. Next, we're going to look at multiplicity or splitting. What is the rule we need to know with splitting? n+1. Where n is our number of neighbors. So A has how many neighbors? 0. We look at our parent carbon, we go over to our neighbor, there are 0 neighbors there. So we would expect a splitting of 1. So that should be a singlet. Hydrogen's bonded to either the carbon or the oxygen. So in this case, we're looking at an oxygen. But with B, we're going to look at this neighbor and there's 0 protons. We're going to look at this neighbor and there's 1. So we have 1 neighbor n+1. So we would expect this to be a doublet. Because they're symmetrical, so they see the exact same thing. You could count from the top if you wanted to. We can count from the top for C, where this is our parent, and we look here, and there's no neighbors, and we look here, and there's 1 neighbor. So this is also a doublet. But because it's symmetrical, you could go from either, but you'll get to the same answer. So what about D? Yes. So when we look here, we have no neighbors. When we look here, we have no neighbors. But when we look here, we have 3 neighbors. 3 plus 1, it will be a quartet. E, I'll use a different color so it's not confusing. But we have our center, we only have 1 neighbor, and how many protons does this have? 1. So E should be a doublet. Now our last signal here, F, it also has only 1 neighbor, which has how many protons? 0. So what kind of signal would we expect? Singlet. Yeah.
So the line that comes off a carbon and then triple bond into another carbon and then to another carbon with the methyl group.
Yes. So really, we have all the information we need at this point because all of our signals are unique. Actually, haha, JK. Not all our signals are unique because we have 2 3-proton singlets. So our 2 proton singlets, 2 3-proton singlets. We have this one and we have this one. So this is where we need our chemical shifts to tell us which will be which.
Do you need to look at the chart, or can you just say because the one on the left's BIOS?
I would use the table just to be certain. But if you feel super confident in your electronegativity chemical shift effect guesstimation, by all means, you can guesstimate.
Is very unconfident at looking at tables.
Okay. Yes, so chemical shift in general has been determined by many chemists before you, and they have figured out how different carbon chains affect the proton shift in an NMR. And so that's where you get the general rule of thumb that comes with the table. But that table is not super accurate because any electronegative atoms, any other carbon chains can shift that chemical shift, can change that chemical shift. And it will always change it in the downfield. So that means that the number will be higher. So we can now look at our chemical shift, which I would have to pull up the table for. But that table will be given to you. You don't have to memorize what chemical shifts mean what. And I think the table is in lecture 14 if you want to familiarize yourself with it before the final exam, for those of you who may feel unconfident with tables. Which I have it pulled up on my computer, but I don't know the best way to show it on the Zoom call or on the screen. But it's lecture 14, slide 9. So I'll make a note of that. So we can go through our different protons that we have here and get an approximation of our chemical shifts. So we can find an ether as 3.3. Our aromatics will come out between 6.5 and 8. We have in a carbon chain, it will be 1.55. I'm running out of space here. Methyl is about 0.85. So now we have extracted basically all the information we could possibly get out of this structure. So now we can shift our attention to the actual spectrum that we were given. I'm gonna do a really poor drawing of the spectrum just to help us identify. So here's our spectrum. We can now match up the signals with the information we learned from our structure. So looking at signal A first, we expect signal A to be a singlet with an integration of 3H. And we have another singlet with an integration of 3H. But the difference between these two chemical shifts is that this is 3.3 and this is 0.85. So when we look here, we have one that is like 1.8, and we have one that's like 3.3. So do we think it's going to be the left one or the right one? Left. Because the chemical shift of an ether proton is a lot more downfield than that of a carbon chain. So we expect this one to be A. So next, B and C, we're looking for two doublets in the aromatic region. And would you look at that? We have just two doublets in the aromatic region. So we know that these are B and C. You don't, but you could take a pretty strong guess because electronegativity will push which one more upfield or downfield? B. So if you wanted to get real exact, you could say that this one is B and this one is C because B is closer to that oxygen atom. So next is D. D, we're looking for a one proton signal that has a quartet. Look at that. We only have one of those. So we can match those up. E, we're looking for a doublet with an integration of 3. We only have one of those. And we only have one signal left. And they go together, and we can double check that because we know that the integration should be 3 and that we should see a singlet. And that's NMR. Yeah.
It's like that good enough for labeling.
Yes. You definitely don't have to like write out all of these steps and like draw on the structure so much. Just label each signal and then label the peak that goes with that signal. And then you can do this kind of like detective work that goes through these 5 steps off to the side. But
will we be expected to like label? You think, or like if you know what all you do is put the A and the A?
yeah, the label is like really the bare minimum. But if you want to try and get partial credit, you'll want to put out like your thought process so that I can see, okay, here's where we lost you. And I can try to get you partial credit rather than all of your labels are wrong and I don't know what you were thinking, so I can't give you any partial credit. Yeah. you use both. So if it was a situation like this, actually, if it was like this and we were looking at this center carbon, we would look at this neighbor, which has 3 protons. We would also look at this neighbor, which has 1. And so these 2 protons, so we would expect a 2H integration. They would have a splitting of 3 from here, 1 from here, plus 1. So we would have a quintet splitting. So that would be like a 5. I would say anything beyond a quintet, you can just label as a multiplet. And that's where it's like so many signals that it's hard to tell. Other questions? Okay. Plays it. So Claisen reactions are going to look quite similar to aldol reactions, but they use esters. So that can be an ester or a thioester. Either will work. And when you do a transesterification, that's when you're switching what the ester is attached to. And that's like a type of Claisen reaction. So, to do an example. The things that you should recognize with a Claisen reaction are going to be those esters. So for this, we'll do a thioester. And a thioester basically just means that you have that double bonded oxygen and a sulfur attached to the same carbon. So Claisen reactions, they require an ester of some kind and base. So our base is going to come in and deprotonate, which is going to create an anion. The anion will always be created adjacent to your acyl because it has the stabilization from the resonance of that double bonded oxygen. So like our resonance can push electrons up. So the deprotonation will always occur adjacent to your acyl. You're then going to need a second ester. We will use a normal ester for this. This negative is going to attack the slightly electrophilic center of our carbonate and push those electrons up onto the oxygen. So we can remember with our acyls that because of the electronegativity, we always have that kind of positive center and kind of negative center. And that makes an electrophilic site for our newly created nucleophile / anion to attack an electrophile. And it pushes the electrons back up onto the oxygen.
So the ester is a type of base.
Yes. So this is the structure that we have now. This is what we would call a tetrahedral intermediate. So this center is called a tetrahedral intermediate. And it's because that carbon now has 4 things attached to it. So remembering our Vesper geometry from beginning of the year, that's a tetrahedral center. Tetrahedral centers are pretty unstable, so it's going to collapse pretty easily. Your negative is going to come back into the system, and you're going to kick off your other ester part. So when we push those electrons back up into the system, it's going to overload that tetrahedral center. Those electrons have to go somewhere. Now, if they went this way, they would kick off a carbon group. Not a great leaving group because you would generate a carbon anion. Not super stable. If we went up the other way, we would just undo the reaction we just did. So really the only option is to go onto the oxygen, because as an electronegative atom, it's a little more secure in holding those extra electrons. I don't know why that looks so ugly, but it'll have to do. So we're left with this little piece. That's this piece is here. So the final step in our Claisen reaction is to neutralize that. So we had that base all the way at the beginning, right? We can steal our proton back. And this remains the same. We didn't do anything to it. But now we have this.
So the whole time, the base and the hydrogen are just like.
If it helps to think of all your bases as water, you can do that.
Isn't it necessarily?
It could be any hydrogen. It is not necessarily the same hydrogen. Actually, the chances of it being the same hydrogen are like really rare because all the solutions are mixing about. But yeah, that's Claisen. Ta-da. So with an aldol addition, you end up with one reaction product where you've like clicked the two together. But with a Claisen, you had to kick off a leaving group. So you'll have like a major product, and then you'll have the little leaving group like side product. Mhm. My office hours during the day are 3 to 4, and my office hours in the evening will be 7 till you guys stop asking me questions. Which was surprised about the turnout tonight. There's a lot less of you than I thought there would be.
Finding the chairs and stuff. I said that simple out.
They accepted defeat. They were like, we're gonna get it 12. We're not even studying.
There haven't been a lot of people drop.
Because if you do one single test, you pass.
So true. That's okay. Exactly.
Make it to make it. Exactly. If I stay on LeBron, I'll get lost last night. If I say I'm dead. What did you say?
Other questions? Yeah.
I think I forgot. I think.
Hey,
I come
I have
back-
office hours tomorrow too. So if it comes back to you. The ones in the afternoon will be upstairs. I think 2125 is the correct room, but truth be told, don't know. Yeah, that's the 3 to 4 one. The evening one will be right back here in the auditorium. Because
The stairs on the other side, you can see right through the window.
this is
That's
true.
how I always remember when I was.
Yeah. But the evening ones are in here because the first time I did an evening one, there were way too many people in the room and I kind of freaked out and then we had to move down here. Guys, you're done so early today. Proud of you. Yeah. Sleep good. Maybe. I don't take classes in the same way that you do.
Yeah, do you have any take homes or anything like that?